Hey everyone, let's talk about instantaneous velocity. If we've already discussed average velocity, which is total displacement over total time, then instantaneous velocity is velocity, well, just like it sounds, at one single instant, or you could think about it as a velocity at such a vanishingly small period of time that it may as well be at a single instant. An instant being a very tiny period of time. I'm going to move me over here. Sometimes the average velocity is all we need to know about an object's motion. For example, a race along a straight line is really a competition to see whose average velocity is the greatest. The prize goes to the competitor who can cover the displacement in the shortest time interval. But the average velocity of a moving object can't tell us how fast the object moves at any given point during the interval. If we're measuring somebody's speed, like say for example we'd like to catch a car speeding, if we measure, say, an interval of time and we measure a distance over which it travels or a displacement over which it travels, we don't really know that it was going under the speed limit or under, at every segment of the journey. We would have to keep looking at smaller and smaller segments to really see if the car was speeding at any particular point along the way. Speaking of which, average velocity is defined as change in position over time. This tells us that the average velocity for a given length or span of time. If we want to know the speed or velocity of an object at a specific point in our time, with this radar gun, for example, we want to know the instantaneous velocity. Watch what happens when we look for the instantaneous velocity by reducing the amount of time we take to measure displacement. Well, what do you think is going to happen? If I have a displacement of 100 meters in a period of 10 seconds, that tells me that the velocity is 10 meters per second. Okay, so that should not be surprising. And if we find there's a displacement of 10 meters in 1 second, oh, well, 10 meters divided by 1 second, well, it's still 10 meters per second, though over a shorter span of time. And we could just go crazy with this, reducing the time and the displacement so as to get the same velocities over ever smaller intervals of displacement and time. And here you see we've taken it to its illogical conclusion, but when say the policeman points the radar gun at a car going down the highway, when he takes that measurement, for all intents and purposes, it is an instantaneous velocity measurement because the interval of time is so small that the car couldn't possibly change its speed during the interval. So it's actually a pretty close approximation to an instantaneous velocity. To describe the motion in greater detail, we need to define the velocity at any specific instant of time or specific point along the path. Such a velocity is called instantaneous. Note that the word instant has somewhat different meaning in physics than in everyday language. Instant is not necessarily something that's finished quickly. We may use the phrase, "it lasted just an instant," to refer to something that lasted for a very short time interval. Instantaneous velocity. In physics, an instant has no duration at all. It is vanishingly small. One of the most common examples we can use to understand instantaneous velocity is driving a car and taking a quick look on the speedometer. At this point, we see the instantaneous value of the velocity. Okay, oops. Instantaneous value of the velocity. The instantaneous velocity is the same as the magnitude of the average velocity at the time interval becomes very, very short. So velocity is change in position, or I don't know, we might say displacement over the change in time as the change in time approaches zero. Notice I don't say change in time equals zero. Okay, that would not be allowed. That would leave us with the embarrassing situation of having to divide by zero, and you know, quite frankly, we couldn't really change our displacement in no time. The graph below shows velocity versus time. How do you know the velocity is constant? Well, as time changes, velocity remains exactly the same value. There is no change. So for all time, or at least the time on this graph, it is not changing. Constant. The graph below shows velocity versus time. When is the velocity increasing? Well, we look at the slope here. Here we have a positive slope. Here velocity is increasing. When is it decreasing? Well, over here we have a negative slope, which implies that the velocity is decreasing. And when is it constant? Well, whenever we have the velocity at an unchanging value, whether it's here or this little snippet down here, it's not changing, and that's a constant value. Okay? I hope everybody can read a graph and interpret what's happening with the velocity there. So, getting greater, remaining the same, getting less, remaining the same. Use the graph to determine the average velocity in A. Well, for A, it always seems like it's 1. So it's really the only velocity, right? So in A, the average velocity is just going to be 1 meter per second because, quite frankly, it's the only velocity. Okay, use graph B now to determine the average velocity of B. And at first they want 0 to 1 second. So at 0, it's 0 meters per second, and at 1 second, it's 4 meters per second. So what I'm going to do is I am going to say that the average velocity is equal to V initial plus V final over 2. So V initial is 0 meters per second. V final is 4 meters per second. I'm going to divide by 2. And on average, in that first second, we're traveling at 2 meters per second. Okay? And then from 1 to 3 seconds, well, that's just a constant value, and initial and final would both be at 4. So from 0 to 1 was 2. From 1 to 3 is 4 meters per second. And from 3 to 4, well, it actually goes from 4 down to 0. So on average, from 3 to 4, we have an average velocity of 2 meters per second again. And then they want to know from 4 to 5. So the average is VI plus VF over 2. Initial is 0 meters per second. Final is minus 4 meters per second. And the average is minus 2 meters per second. So that's going to be minus 2 meters per second. Okay, and now what? Oh, from 3 to 5 seconds. Well, this will yield a very interesting result. It's going to tell us that if my initial velocity is 4 at 3 seconds and minus 4 at 5 seconds, well, let's see, 4 meters per second plus minus 4 meters per second over 2 is 0 meters per second. So I've spent as much time going one way as going the other and at the same range of speeds. So the average speed from 3 to 5 is actually 0 meters per second. Use the graph to determine the instantaneous velocity at 2 seconds. Well, 2 seconds, it's the only velocity. It's 1 meter per second. Okay, at B, it's going to be 4 meters per second. So for instantaneous values, I just read off the graph where it intersects the time for which you're looking. Okay. When the velocity of an object is a constant, the instantaneous velocity is the same as the average. Yes. When the velocity of a moving object changes, its instantaneous velocity is different. Okay, when it's instantaneous, you actually have to read off the graph where you're looking. Okay, and that's instantaneous velocity. I hope that made sense.